Hello again. In this video, we're going to go over this example where we have motion in a gravitational field. So it says, suppose a stone is thrown vertically upward with an initial velocity of 64 feet per second from a bridge 96 feet above a river. By Newton's laws of motion, the position of the stone, measured as the height above the river after t seconds, is s of t is equal to negative 16t squared plus 64t plus 96. Where s equals 0 is the level of the river. And then part A says, find the velocity and acceleration functions. Now, of course, in this example, we have a stone that is being thrown vertically upward. And so we have one-dimensional motion vertically, which can be represented with a vertical number line. And this position function tells us the position of the object on that vertical number line at any given time t. Okay, and so what we want to do is find the velocity function and the acceleration function. Now remember, the velocity function can be found by finding the derivative of the position function with respect to time. Okay, and so the derivative of this position function would be negative 32t plus 64. Okay, so that's our velocity function. And then the acceleration function can be found by finding the derivative of the velocity function, which is negative 32. Okay, so that's part A. We have the velocity function and the acceleration function. Okay, part B says, what's the highest point above the river reached by the stone? Now, of course, the initial position of this object, this stone, when t is equal to 0, you can see when you plug 0 into the position function, you can see that you get 96. So that's the initial position of the stone. It's at 96 feet above the river. Okay, which is at the 96 foot mark on this number line. And then, of course, it's thrown upward, and so it moves up, but at some point it stops. It reaches its highest point, and then it comes down, and eventually it'll strike the ground. Okay, so what we want to know is what is the maximum height of the object. Okay, so let's see how we can find that. Now, the way we're going to figure this out is when the object reaches its maximum height, it actually stops. It has 0 velocity at that moment in time. So what we're going to do is we're going to take the velocity function and find out when it's equal to 0, at what time it's equal to 0, and once we know the time that it reaches its maximum height, then we can plug that time into the position function and find out what is the position of the object on this number line at that time. Okay, so for part B, we first need to find out when the velocity is equal to 0. What time does the velocity equal 0? So let's take the velocity function and set it equal to 0. Okay, and then we're going to solve for t. Of course, you can do that just by subtracting 64 over to the left side and then dividing both sides by negative 32. Okay, and so that gives you t is equal to 2. Okay, so it takes it 2 seconds. It takes 2 seconds for the stone to have a velocity of 0. And that's the point at which it's reaching its maximum height, because it stops once it gets to its maximum height and has 0 velocity. Okay, knowing that, we can now take this time and plug it into the position function to find out where it's located on the vertical number line. Okay, so now we just need to find s evaluated at 2. Okay, so just plug 2 into the position function, and let's see what we get. So 2 squared is 4, and then 4 times 16 is 64. So that's negative 64. And then 2 times 64 is 128. Okay, and then negative 64 plus 128 is positive 64. And then you add that to 96, and that gives you 160. Okay, so S of 2, S evaluated at 2 is 160 feet. And so that's its maximum height. And you can see here, here's the graph of the position function. And right when t is equal to 2, that's when it reaches its largest value for S. In other words, its maximum height. Okay, now part C. With what velocity will the stone strike the river? So of course, eventually this stone comes back down and then strikes the river. And we want to know what the velocity of this object is right when it strikes the river. Okay, so how are we going to do this? Well, we have a velocity function, right, which describes the velocity of the object at any given time. And so the only thing we really need to do is to find out at what time is it striking the river. Because once we know what time it strikes the river, we can take that time and plug it into the velocity function to find out what its velocity is. Its instantaneous velocity. Okay, so all we really need to do is find out what time it strikes the river. But when it strikes the river, it has a position of 0 on the number line, right? So S is equal to 0 once it strikes the river. And so we're going to take the position function and then set S equal to 0 because it's striking the river when S is equal to 0. And then we're going to solve for t. And then once we know what t is, we can plug that into the velocity function to find out what its velocity is at that particular time. Okay, so let's take the position function and then set it equal to 0 and find out when that happens, right? When does it strike the river? Okay, so that gives us this equation here. And you can see that this is a quadratic equation. And the first thing you might want to try is to factor this. So first thing we should do is pull out the greatest common factor. Okay, and I believe you can pull out a 4 out of each of these. In fact, I'm going to pull out a negative 4. Okay, and that leaves us with 4t squared minus 16t minus 24, because 4 times 24 gives us 96. Okay, and notice since I'm pulling out this minus sign, the sign changes for each of these. So this is a plus, and this is a minus, and this is a minus. So actually it looks like we can pull out another 4. So I'm actually going to pull out another 4. And that leaves us with t squared minus 4t minus 6. And so we're actually pulling out a 16 overall. Okay, so you could have just done that right off the bat, since there's a 16 in common with each of these. Okay, so pull out negative 16 from each of them, and you'll be left with this. And of course, you can just divide both sides by negative 16. And this, of course, will still be 0. And you're left with this quadratic. Okay, and then you might think about factoring this quadratic. So you need two factors of -6 that add up to -4. And if you go through all the possibilities here, there aren't two factors of -6 that add up to -4. And so this does not factor. And so the only thing we're left with is the quadratic formula. Okay, and so in this case, A is 1, B is -4, and C is -6. And so let's just plug those into the quadratic formula. So we have minus B plus or minus B squared minus 4 times A times C. And that's all divided by 2A. Okay, so that leaves us with positive 4 plus or minus 16, and this gives us plus 24, all divided by 2. Okay, and then if we continue to simplify this, that gives us 4 plus or minus the square root of 40, all divided by 2. And you can reduce this square root of 40 because that's 4 times 10. And the square root of 4 is 2, so that leaves you with 2 square roots of 10. Okay, and then if you divide both of those by 2, you're left with 2 plus or minus the square root of 10. Now let's go ahead and see what that is on the calculator. So we do get two answers here. So let's look at both of them. We have 2 plus the square root of 10 which is about 5.16. Okay, and then we also have 2 minus the square root of 10, which gives us negative 1.16. Okay, so obviously time cannot be negative. So the answer in this case must be the positive 5.16. Okay, so now that we know what time, that's the amount of time it takes for it to strike the river. Okay, so then the last thing we need to do is find out what its position is. Okay, again, t was approximately 5.16 or negative 1.16, but we're eliminating this as a possibility because it doesn't make sense in this physical context. Time cannot be negative, so it's got to be the positive case. But then that's the time it strikes the river, and so let's go back to the position function and then plug this in for the time to see what it's, I'm sorry, not the position, the velocity function, right? We're trying to find the velocity. So let's go to the velocity function. And remember, the velocity function was negative 32t plus 64. And then we can plug the time into there to find out what its velocity is. Okay, so negative 32 times 5.16. And to be completely accurate, I'm actually going to write as many decimals as I can. 2277766 plus 64. Okay, so that gives us about negative 101.2, and I'm just going to round that off. And this is going to be in feet per second. Okay, the position is being measured in feet and the time is being measured in seconds. Okay, so the velocity should be in feet per second. Okay, so let's just talk about this. The negative indicates the direction that the object is moving. Remember, velocity is a vector, so it has both direction and magnitude. And for one-dimensional motion, it's sufficient just to tell us whether it's moving in the positive direction or the negative direction. So in this case, it's moving in the negative direction. Which makes sense because on the number line, the negative direction is downward. And that's exactly what's happening because the object goes up, it stops, reaches its maximum height, and then it starts to move downward. And as it moves downward, it has a negative velocity. So that makes sense because when it strikes the river, it's moving in the downward direction. Okay? Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.